I think we'll go ahead and get started. So my name is Mike Fisk, and I'm I guess the coordinator or facilitator for this breakout session. I don't know how many of you supported the session on space manufacturing or this morning. It was kind of a attendance was good. The number of questions was kind of low. That doesn't surprise me since this was more or less a science focused workshop, and at best that session was kind of applied science, more toward the hardware end, but it did, or maybe or tools required to do some experimentation, but it did bring up a couple of needs that in my mind are very critical for the agency as we move forward toward landing on the moon. And a couple of the papers address one of them, and that is development of simulant. One of my things I keep kind of harping on to our management, I know they understand it, is the need for large quantities of high fidelity simulants. Now, I also understand that a really high fidelity simulant is going to be very expensive, but and not. I guess the fidelity kind of depends on what the application is, and maybe a higher chemical fidelity is required for processes that react with regolith, and perhaps a mechanical fidelity is more important for other applications. Certainly those that require, abrasiveness, for example. So I just want to kind of throw out a question in terms of the work that various people are doing. What kinds of quantities of simulant do you kind of anticipate needing in the next, 2 to 3 years? Jennifer Edmondson, one of my colleagues, is on this call, I believe. She's a member of the simulant development team for the agency. There may be others as well. So I'm sure she'd be interested in hearing some of your thoughts as well. So kind of open it up, see if anybody'd like to jump in and talk about your long-term simulant needs. Okay, maybe I'm overestimating the agency's simulant needs. But I don't think so.
Okay, so let me turn this light on so everyone can see a face. Hi, my name's Jesse Silverberg.
Hey, Jesse.
Multi-Scale Systems. We are a small business started in 2018, focused on development of technology from university ecosystem on what are called mechanical metamaterials. And the basic idea is that we use geometry to engineer material properties. We think this might be useful in lunar applications because you have some limited amount of in situ resources, but using geometry to engineer material properties allows you to achieve a greater variety of material, functional material properties from a limited amount of resources. So from our end, we're thinking ahead towards product development. And what would be beneficial for us is if we had materials that we could be consuming to be starting to develop those products. There was discussion earlier in the day about spares, and there's a great little mnemonic thing.
Spares and space repair, something like that.
Spares and repairs is perfect,
yeah.
Right? When an O-ring breaks, if it's made from a polymer, a petrochemical polymer, maybe made from something else, right? But if an O-ring breaks, you're not going to be able to make a petrochemical-based replacement on the moon. You've got to ship it. So starting to think about how you can get some of that functionality from the materials that are available is where our headspace would like to be. But what's the thing that we can be working with today that would give us an idea of how to design a product for tomorrow? So I don't know I have an answer to your question, which is where the quantities, but I know that if it was available at reasonable market prices, we could be developing products right now.
Yeah, yeah. There's a whole in space, and this is what Corky was referring to in his presentation this morning. There's a whole group at Marshall focused on in space manufacturing, and um, one of the things they're looking at, I mean, the motto of that group is "Make it, don't take it." And so when we first go up there, and obviously the demonstrations are taking place on station. When we first go up there, we're going to have to take raw material with us. If we're going to do multi-material 3D printing, we'll have to have aluminum, maybe not aluminum, steel powder or Inconel powder. And, if something breaks and you go fix it. And if it's, um, for station or even moon, it's maybe not critical, but for long duration missions far away, the importance of that capability goes up exponentially. So the ability to extract materials from this, we'll say the real issue will start probably with Mars, but to be able to extract elements from Martian regolith, which is about the only, solar power in Martian regolith is about all you got there. Be able to extract elements from there and either develop your own materials, carbon sources from recycled polymer waste, whatever the case may be. I agree with you. It's critically important for a sustainable presence. So another group at Marshall's looking at ionic liquid extraction of various elements from regolith, where you could basically have a regolith feedstock that's processed through a number of chambers with different ionic liquids that selectively extract different elements, and then you can take those elements and mix them back together to make a binder, for example, for a concrete or an alloy, maybe not as complicated as an alloy we would make on Earth, but an alloy that you can then do something with, process it to turn it into filament that you can print with, or that's got to be the long-term vision, hopefully demonstrated initially on station and then on the moon, before we go to Mars. So agree with you for sure. The need is critical. Jennifer, you want to touch on that at all? Thought I saw her.
No, you're absolutely right.
Yeah.
The need is critical.
Anybody else have thought about long-term needs for accurate simulants or other resources on the lunar surface?
Mike, you have a comment in the chat.
Oh, I do? Let's see.
Mm-hmm.
Oh, wow. Is that?
Yeah, it's me. So we are a research group from University of Alberta in Canada. And our focus here is to finding ways to use human waste or any other waste that is produced on the in space. For example, human hair in International Space Station. For example, now human hair is disposed. It's collected and disposed. We would like to use that to extract keratin and finding ways to use it as a polymer for 3D printing applications. This is one of the things that we can do. There's one more thing that can be done is on the International Space Station as of now. For example, the clothing that the astronauts use are not cleaned on the International Space Station. They are shipped back to the Earth. So it's a logistical problem. So if we can find ways to use that as a building material or a building source, that would be a good long-term plan.
Excellent suggestions. That's the first time I've ever heard of the possible use of human waste other than actual human waste. We all saw The Martian, so we know it can be done. But as another resource for manufacturing, the use of hair to extract keratin, very interesting. I'm also, and this is probably, if anybody here is an architect, this is probably heretical, if that's the right word, but I'm also, I realize that probably the Apollo landers are all historical artifacts at this point. But when we start landing frequently, especially when we have two-stage landers, they land and they take back off and they leave a big hunk of metal sitting on our landing pad, which we have to move off so somebody else can land there in the future. And two, it's excellent feedstock material for, metals processing. You don't have to extract all that metal from regolith. It's out there with it. You just go out and cut it up and melt it. But every time I say that, people look at me like those are historical artifacts. We can't touch those.
Hey, Mike, I think you can add a 3 to that. If it's going to be a sustainable, long-term endeavor, we can't be just leaving a bunch of abandoned junk from an environmental perspective all over the lunar surface.
No, that's right. Yeah. Getting rid of it is the other benefit. Use it as some kind of feedstock, and that gets into I don't remember who mentioned it, but designing for a purpose. So, you've got a lander leg that you plan to leave on the moon. Well, if that leg is designed such that it can be disassembled off a lander and subsequently used as part of a support stand for regolith for an unpressurized shelter, for example. I mean, it was designed for that. That requires some pretty good integration between NASA and contractors and between contractors, since somebody's building the vehicle and somebody else is designing and building maybe the habitat or whatever. But there's a real opportunity there, I think, and we've talked with, for example, the human lander folks, and right now they're not even thinking about, we know that long term, and this was a genesis of a question I asked earlier this morning. Long term, once a settlement site has been established, one of the first things we're going to fabricate is a landing pad, because of the possibility of ejecta under a landing vehicle doing serious damage to a habitat that's or another vehicle or whatever that's anywhere near close to the lander. But with a landing pad, you can mitigate that. So the ability to print a landing pad relatively close to your settlement site and relatively fast once the settlement site is located is going to be important.
Hi, Mike. I'll speak up here now that I've finished my lunch. Can you hear me?
Yes, I can, Paul.
Yeah, my name's Paul Furrier. I'll put my video on briefly there and then turn it off. I'd like to answer your first question. You asked how much regolith, high fidelity regolith is needed. So anyway, by the way, I'm from New Mexico Tech, and I am the faculty advisor of Josh McDuffie, who talked earlier on dry aerosol deposition of regolith.
Oh, very good.
So I'd like to talk about a few things. First, I'll answer your question. As we're ramping up our process now and getting greater and greater success and getting more and more excited about it and what we can do, the possibilities with in-space manufacturing, we anticipate using on the order of kilograms a month, and then if we scale up larger, tens of kilograms perhaps a month. I envision if things go great, and we scale up to larger machines. I'd like to follow up my students' talk, by the way, because sometimes students are tired and don't exude enough enthusiasm in their talk. If Josh is listening, no, okay, sorry, Josh. But I know most of you all may be interested in forming bricks and large bulk structures. But if you recall, Josh's talk was on coatings and additive manufacturing of coatings. I would like to make people aware of the promise and the excitement for our process. Dry aerosol deposition. Again, we can take, and several years ago I got excited looking at Apollo samples of regolith and saying, hey, that's a particle size distribution that could work great in our process. Dry aerosol deposition is a new additive manufacturing process, and it has not been described as additive manufacturing previously, but that is what it is. It's a coating process, and it's a way to put down ceramic materials at room temperature with no thermal energy input, no binder, nothing but kinetic energy. And so maybe some of you gathered that from Josh's intro slide. Okay, so we can use regolith as is to build significant coatings, significant thickness. And by the way, they're fully dense, no porosity, nanocrystalline, which yields, as Josh implied on his properties slide, unique combinations of properties, meaning extremely high hardness and at the same time a low elastic modulus. That means it's a compliant and hard material. Now that's strange, and yeah, that's what nanocrystallinity does for you. Okay, so we're starting to explore micrometeoroid impact protection from these coatings. And when you start talking about repair and when you're talking, what was it, spare and repair, repair work on surfaces of space vehicles, repair work on habitats, creating protective coatings on habitats, coatings, fully dense coatings on other structures that have been talked about on the moon. This is the process and so I'd like to get people excited about this and aware of it. We are essentially the only university facility in the country that can do this process, by the way. And I'd like to, anybody that this does sound interesting for, call your attention to our publication in late last year in additive manufacturing, where we presented our first depositions of regolith material on a variety of substrates. And the applications are myriad, from impact resistance to radiation protection, thermal protection, and even electronics, by the way. I've got other projects going on where we can do on-site, we can dream about on-site additive manufacturing of hybrid electronics. For instance, we could use the regolith as a dielectric material. By the way, we can use the same process to deposit metals. So when you talk about in-space, on-location manufacturing, we've got a lot of dreams and a lot of big ideas. So anyway, I'll shut up, and with that, if the Exolith lab is still listening, we're going to be needing kilograms a month, we see in the near future. Also got some ideas for them on how they might characterize the flowability of their materials, if any of those students are still listening. So anyway, okay, thanks.
Hey, Paul, appreciate those comments. As a matter of fact, you've piqued my curiosity. I was thinking about it actually a little bit from the presentation, and there's a question related to that. Can the coatings be applied in a vacuum?
In fact, they need a vacuum. That's
I was going to say, I wondered about that.
Yeah, my first proposals to do this work, I said, so you see, on Earth, we need a vacuum chamber. It's just a rough vacuum, okay? But I said in my proposals, the universe is our chamber. So the vacuum, that's what we need. Now on the converse side, flip side, we need a delta P. We need a pressure gradient to accelerate the particles. So there we need compressed gases.
Yeah. So I'm throwing this out to the general public because it's something we're doing, and I'll put my email in chat if you want to get back with me later, or anybody wants to get back with me. We're planning to do a series of tests on various potential lunar landing pad materials with a plasma torch that's going to be scaled to kind of replicate the heat flux of a lunar lander. And right now there's three, and one's been selected. There were three in contention. I think there's a lawsuit now, another lawsuit by Blue Origin and Dynetics against NASA. I mean, it's the lawsuit, they're suing NASA for the down select that they made. Long story, but anyway, so we're doing this plasma torch testing, and I'd be interested in taking one of our concrete materials, putting your coating on it, and seeing how it withstands the plasma torch test.
Absolutely, yeah.
compared to a control sample.
That'd be very interesting. The thermal response of these coatings has not been tested yet. We don't know what. And again, these are nanocrystalline now. As they're deposited, we're talking a nano material, and we expect at some temperature certainly changes to the coating will take place. Grain growth, okay, and how and when, at what point, let's say cracking and failure of the coating occurs. Obviously, it's going to happen at some point, but we don't know. We don't know.
Yeah, yeah. No, it's very intriguing.
Yeah, dust mitigation, the big issue again. Here, how do you fight dust? Well, you fight dust with dust. How's that? You put a coating material down. Right? What's going to be resistant? What's going to be resistant to attraction of dust? Well, the same composition material itself. The charge transfer has already taken place. So we can put these ceramic coatings. We can do them thin. We can do them thick. We can put them on polymers. We can put them on spacesuit material. Okay, so I'm excited to be pursuing all these opportunities with NASA and other space folks.
That's very interesting. Yeah. Everybody on the call, if you have potential applications, I'm sure Paul would entertain a contact. And Paul, I just posted my information, so if you don't mind, drop me an email, and maybe we can initiate a discussion about these tests.
Yeah, I'll do that.
So while everybody's kind of mulling over the regolith discussion, another topic I wanted to bring up is, and I think I saw DeWitt Burns online, so this is appropriate, is the availability of large-scale thermal vacuum chambers for testing of lunar surface spaceflight hardware. I think it's common knowledge now that Marshall is modifying an existing chamber we call the V20 chamber. It's a 20-foot diameter, 28-foot long chamber into a dirty thermal vac chamber with a regolith bed and the capability of hot and cold temperatures, high vacuum for testing of component level and some full scale level hardware. And it's going to be a real capability. I know JSC has a large chamber. Our understanding is, and it's just an understanding, is that it's going to be primarily dedicated to ISRU testing. And I think there's a real need out there for this capability. So I'll make that one general information if people are looking for an opportunity to do some large-scale dirty thermal vac testing. And you can, Whit Burns is kind of our point of contact at Marshall on that capability, but you've got my name and number there. You can contact me and I can put you in touch with him if anybody's interested in using that, because there aren't many of that capability. There's some other entities that have thermal vac chambers available. I think Paul Van Susanti at, was it Michigan Tech? Jennifer?
Yes.
Yeah, he's, they have a chamber there that's available, I believe.
Hey, Mike, this is Kurosh Ragu from JSC. So that's as you mentioned, so Paul has one in Michigan Tech, has a smaller chamber. The chamber at JSC is a 15-foot diameter chamber. Is the dirty lunar chamber with a dust deposition device system that applies dust. Is primarily for any assigned for the ISRU and surface power systems. So
Okay.
they have various different especially for some of the future fuel cell systems that are utilized in that chamber. So there's various different domains that utilize in that chamber, but primarily it provides a dust soil bin and IC regolith column for drilling. at all, and inside the 15-foot diameter chamber. And that system is within the August timeframe is up and running to provide the services. So this chamber has already been booked by various different programs, ISRU, surface powers, external vendors, suborbital flights, hardware payloads. So, we in process of, we have another 20-foot diameter chamber that we trying to utilize that one for folks that they don't need dusty environment. It is still dirty, but they don't need a lot of dust and stuff. They just want to be.
Yeah, I got you.
So.
Well, that's very good.
I think South Korea, they were working on a horizontal chamber, large diameter chamber with a significant amount of the lunar regolith in it. I'm not sure where they are at with that constructions, but South Korea was another organization that they are focusing on a very, very large lunar chamber.
Okay. And of course, Glenn has the VF-13 chamber.
Right. That's a 4-foot diameter. I think is 14 feet tall.
Yeah, sounds about right. Yeah. Would you say about 4-foot diameter? Did you say?
It's a 4-foot diameter.
Yeah. And it's a vertically chamber.
Correct.
Yeah.
Correct. It's a vertical.
The one at Marshall will be horizontal. It's horizontal. And I'm bringing this up because I think there's going to be a huge demand for these kind of chambers in the next few years. And the more aware everybody is of where you can go to get access to these kinds of services. And as you heard Karush just say, the chamber at Johnson is largely booked up already. So I imagine if there's the second one, if it's coming online, it'll book up fast. I know ours will. I mean, the Impact project alone is planning to has a lot of testing planned in it over the next several years. So I see the demand for dirty thermal vac test capabilities being high over the next few years.
So that's going back to the simulant needs, right? There's obviously Jennifer is here. She's here, and she's a part of the simulant working group. So that under the GCD, we do have a ISRU portfolio that they call it Lunar Oxygen and Water Extraction. Mm-hmm. Under that portfolio, it has, I manage that portfolio for the STMD. We have five projects, five elements. One of that elements, one project is a lunar simulant development. So there's a significant number of the working members that from the various different centers and scientists and geologists that is led by John Gruner. The key performance parameters is focusing on the 3 types of the simulants. We call it the low fidelity, which is a provide the mechanical properties of the simulant. That's a lot of people, they don't really need high fidelity or mid fidelity per se. They want to see how that device works, how the system works, how the regolith moves into the system. A lot of mechanical characterizations. So that's a one, and then we have a mid fidelity type of the simulant formulation, and then high fidelity. The goal of this group is to develop there's a survey that I suggest, we can provide the link. It is open to everyone. You can use that survey Jennifer, if you have that link for the APL survey, if you would, I don't have it in front of me with the chat.
Already in the chat.
Great. All right, I appreciate it. I think Jennifer can really give more details. But the survey is for everyone out there whether it's the government institutes or academia or the companies, they can fill out that survey with respect to their project, tell them what type of the simulants they need for what project, what are the needs are. And so and on a parallel path, the working group is working on a various different recipes and also finding who is the companies or places that they are capable of fabricating this, making these materials. So from that standpoint, then the high fidelity ones are the most, obviously the more timely, it takes a long time to produce it and is the most expensive ones. And then that part is not everyone needs high fidelity ones. But again, our purpose is not to purchase or the purchase simulant for people. We do purchase simulants. We have purchased some NULHT-4M from the USGS. We have bought some OB1 from Canada. We have bought some LHS from University of Central Florida. But in a sense, we are really focusing on developing, on understanding. The part of it is having the same resources or sources to produce the simulants with that quality that they need. So there is a really a traceability. They know all the materials. We know where the source are, and we also have a plan to look at this simulant degradation mechanism. This is something that maybe most of you guys, if you have dealt with this, or they're trying to characterize to understand how long you can use the simulants in your application before that simulants is no longer maintaining its original properties. And after how many use or what type of use you need to go for other batches of the new simulants. So the degradation is a key, another area that the team just already start thinking about to characterize that from that perspective that from different processes the degradation is different, the factor how degradation takes place. So that's another area that they are working on. So I just want to give you some overview of these activities that simulant teams are working with the John Hopkins Applied Science Physics Lab and the rest of the academia and industry. And that survey, take a look at that survey, the link, and it would be really helpful. That's about it, Mike.
I was muted. Sorry about that. Yeah, thank you very much. Those are great comments. And like I said, this 2-hour breakout session didn't really have any specific topics. I figured if we brought up a few that would get people talking, we'd maybe get some interaction and collaboration between people. And I feel like that's already happening, which is great. And we're only 30 minutes in. So we had another comment from the Heather. She just went off my screen. Heather.
Hi.
A guest.
Yep.
Are you there, Heather?
Yep. Can you hear me?
Yes, sure can. I was intrigued by your comment.
Oh, great. Yeah, it looks like some other people had some interesting replies to it as well and was interested in it. So I guess I didn't hear the first part of the conversation. I was in another session, but what I was wondering is, I mean, from the presentations that earlier, one of the things, obviously, greenhouse was mentioned, but one of the presenters talked about, not wanting to bring things like chairs and tables and other furnishings or things of that nature. And it seems to me, and another presenter mentioned about not having a ton of different materials. And of course, so my background is bioregenerative life support systems. We always struggle with, what do we do with the inedible biomass? And I've been looking at different ways to use it, put it back into the system to recover nutrients. But I also think that there's opportunities for using it it as a feedstock for different types of materials. So like one example that we have here on Earth right now that I've seen is things like wheat or straw board. And so it uses, the fibrous materials from grain production and then some sort of a binder to, instead of say making like wood chip board, or particle board. And so I think that there are opportunities like that, as well as, and this might seem a little bit far-fetched, but if we really got to big scale, you think about how, rubber is made, we tap latex, we tap rubber trees to make latex. And so could we find the binder from some other, plant resource, or maybe algae or fungi or one of these other things. And I'm not an expert in this area, but I just wanted to throw it out as a topic to see if there was much being done in the area as something I would be interested in pursuing, and maybe other people are already pursuing.
Well, we got, let's see. We got over 50 people online. I'll bet somebody else out there is interested in that, or has experience. We're all interested in it, but has experience with that. Anybody out there have any thoughts or comments?
And just one other thing to add to that, that's sort of on the flip side, is how do we, for growing the plants, of course, hydroponics is always the thing that you hear about, but I think there's a lot of interest in work being done on using regolith and, adapting it to become a growth media. And so, can you turn it into soil by adding these, organic compounds? But the other question would be, can you also use it to make a reusable media? So in hydroponics, one of the things that's used is like hydroton, which is like an autoclaved clay like ball, or turfus, which is like an autoclaved clay, a different kind of clay particle. So could we do something similar with lunar regolith to create a growth media? Would be another idea to pursue.
Otis, Walton, did you have a response?
No, I don't. I'm sorry. Let me unmute.
Okay. The gentleman we were talking to this morning was also talking about using human, or maybe that was earlier today. We're talking about using human hair and extracting keratin to use possibly in 3D printing, which was pretty intriguing as well. I did want to refer quickly to the chat comment. DeWitt Burns at Marshall just posted a couple of points of contact regarding both thermal vacuum test capability at Marshall and simultaneous, radiation, UV, plasma, et cetera, environments in a smaller chamber at Marshall. And it's Kevin H. Burks at nasa.gov and Mary.K.Nels at nasa.gov. And I'm sure they'd both be interested in talking to anybody that had interest in that kind of testing. Thank you for posting that, DeWitt. Well, for the sake of maybe stimulating a different topic in the conversation, a little bit of my background and what we're doing at Marshall and the Impact Project. A metallurgist by background, developed a lot of experiments over the years for microgravity materials processing. And one of the products that I worked on, or actually my thesis was aimed at in graduate school, was the use of directional solidification of immiscible alloys to fabricate very fine, like almost nanofilters, by controlling the relationship of two immiscible alloys. As you directionally solidify it, you can, and then go back and etching out one of the two materials, you can achieve very, very fine filters. And that was a comment that was asked earlier this morning about, we were talking briefly about fibers. anyway, that kind of sparked an interest to me in space processing, and since about 2005, I've been leading an effort aimed at basically additive construction or large scale construction of surface infrastructure on Moon and Mars. And that turned into kind of a long-term project that has kind of come and gone with some funding over the years, but is now a large project called Impact at Marshall. And we're focusing on development of a number of technologies for potential construction on the lunar surface. So some of the materials we're looking at constructing with include either laser sintered or microwave sintered regolith, actually melting and extruding molten regolith as a construction material. And then there's a number of other extruded materials, including some water-based concretes where the binders can be extracted from lunar regolith. Sulfur concrete has always been a type of waterless concrete. It has its own problems, but we're continuing to evaluate it as well, and a geopolymer concrete as well. So those are all being developed in research at Marshall, as well as we have Icon under contract. Icon is a 3D printing company out of Austin, Texas. They printed the country's first fully permitted 3D home in the United States. They've now printed over 20 homes in both the United States and in Mexico. They are working closely with us on development of lunar hardware to process structures on the lunar surface. And to that end, we've worked with a couple of architects on design of landing pads and habitats that can be additively constructed using, hopefully any one of the 8 materials that I just mentioned. So there's a lot of activity. There's a big need for large quantities of simulant. We have researchers supporting the project from all over the country. The goal is that one of the first structures that we fabricate on the lunar surface will be a landing pad. Some of you may not be familiar with, thank you, Jennifer, for putting Icon's contact information there. On Apollo 12, one of the goals of Apollo 12 was to land near a surveyor spacecraft that had landed previously in 1967. So in 69, when Apollo 12 landed, they wanted to get close enough to go over and take some of the hardware elements off of the surveyor spacecraft, bring back to Earth, and evaluate for atomic oxygen degradation, micrometeorite hits, etc. And when they got there, they realized that all the surfaces facing the Apollo 12 spacecraft had basically been sandblasted by the ejecta coming from under the craft as the descent engine was firing. And of course, all the Apollo missions described significant ejecta and cratering underneath their spacecraft. Now, there's been lots of research done on that over the years. We now know that the highest velocity ejecta is close to the surface of the moon. I mean, the lower the angle, the faster the ejecta. The higher the angle, more it's just lofted. But some of that, especially as we start talking about higher thrust engines, larger landers, we know some of that dust can actually be ejected into low lunar orbit, which is problematic for subsequent landings, for Gateway, anything that might be in orbit around the moon. So that problem has to be mitigated, and mitigated very early, and that's why we think a landing pad is going to be the first thing that we fabricate on the surface. So we're focusing on that. I mentioned earlier we're doing some plasma torch testing to simulate a descent approach on various materials to see how they behave. We don't feel that compacted regolith is going to be sufficient in this application because of the such high kinetic energy temperature associated with these exhaust plumes. And to the extent that while some of the other landers, their engines are fairly close to the surface, clearly demonstrating the need for a pad. The Starship, the SpaceX Starship, is so large, and the thrust from those Raptor engines is so high that if they tried to land with those engines, they would just dig a crater under the vehicle and probably not be able to land. That's why they've put a ring of like 24 thrusters around the vehicle, about 2/3 of the way up from the bottom. And as they approach the lunar surface, they turn off the main engines and use those thrusters to approach. So the thermal profile, the thrust profile of Starship is completely different than that of other landers, the CLPS landers, HLS class landers. So if you couple the mass of a Starship with the thermal environment of a Blue Origin or Dynetics lander, put some pretty significant requirements on a lunar landing pad. Very challenging. Let's see. I think, Heather, did you have your hand up still? Did you have a follow-up question? Oh, okay. Anybody else have? Uh-oh, there we go. Anybody else have questions or? The reason I went through that whole discussion about impact and what we're doing is just to think if there's anybody who's interested in potential collaboration. We do have, we are working with KSC. They are the lead center for excavation, and so we obviously interface very closely with them. They have the requirement to do the excavation and site prep for whatever we come in and build. And we also interface obviously very closely with ISRU because they will be providing a lot of long-term, a lot of the feedstock material to us. Some of it is just, regolith that might just be processed, but other feedstock could include various quantities of metal elements to mix together to make a binder, for example.
Mike, we call it tailing, the tailing of the ISRU, whatever comes out of the ISRU processes depends to the locations, provides additional materials for processing.
I hear some hammering, Karush. Is that behind you?
No, I was going to say.
Okay, there's an open, if you have an open mic, please close it just for a moment. Can you repeat that?
Yes, I said we call it the ISRU tailing. What it is, when the process is complete, you have materials coming out, whether it's the water extractions, oxygen extraction. So those materials are, now they have various different properties. Some of the stuff has been removed, or the temperature profile of them different, so they can be used for various different applications for additive, for the construction and the additive manufacturing. That's for the South Pole area. If you go obviously in the Mare section area, that's there's other it's the locations provides a different type of the materials. Obviously in the Mare areas, because of the iron oxide, one of the area of the beneficiations is a critical technology to perform the beneficiations for metal extractions. So those are a lot of technology that KSC, beneficiation is a KSC aspect of it, working on. And so to your point, ISRU plays a major role from providing materials. Materials already been processed and are in a different form, different shape, different temperature profiles that can be utilized to reduce the amount of the energies required to change those characteristics of those materials. So there's a lot of synergy. Obviously, at all of this, center of all of this is a power requirement, which, as you know, everybody needs power. So none of this can be done without the power. So the power is a long haul. So that's a lot of domains, right? Activities, ISRU, excavation, transport, material transportations, rovers. Everybody's working with right now. Start working with the power system team, power generation team for surface power. to start that coordination, because don't lose the sight on power requirements, because power
no.
is
Huge
important. So,
constraint.
yeah, huge
Yeah,
constraint. So
I
make
don't,
sure everybody is aware of it. So you come up with the technology, right? But at the end, the power is the center of everything. So.
yep. I don't represent the official NASA position. I'm not even sure actually what it is, but I'm a huge advocate for nuclear surface power. I think that if we're really serious about long-term, presence on Moon and Mars, we have to go to a nuclear surface power. So sometimes I use that as my criteria. If I see, early on, obviously, when I see solar power referenced, I get it, because it's the quickest way to get up there and land right now. But long term, I think we have to consider nuclear. But I appreciate your comments. Let's see, there's a comment, there's a chat going on in the chat box about fibers. That came out of a conversation this morning about one of the things we've been looking at is in the impact project is many years ago, I'll say back in the 2005 timeframe, when we were talking about lunar concretes, we developed a fiber puller, kind of threw together some old parts, made a fiber puller, melted regolith, pulled hundreds of yards of fiber. Now we coat it with a polymer to just kind of stabilize it, and you could bend it, around about a 18-inch spindle, but it was fairly brittle. And when the funding was cut back in about 2007, somehow that fiber puller ended up getting excessed, which, it happens. But we are now in the process of we're working with a local community college to design and build a new fiber puller, a replacement, and that'll be hopefully done in a month or month and a half. And we're planning to we took some of the older fiber and basically chopped it up and mixed it up with concrete to evaluate strength. It did positively affect overall strength, although it is, like I said, it's somewhat brittle. But it was a marginal improvement. That's the only application we've looked at that fiber for as of right now. But there was some questions about using them to make some kind of a filter media. Is it Gareth? Is that how you pronounce your name?
Yeah, sorry. I've been putting my hand up and down for a bit and then kind of like letting the conversation
I'm sorry.
move on. No, it's all right. It's all right. It's just the nature of thing.
A lot of different topics, but I'm intrigued by this. So why don't you go ahead and describe what you're thinking about? And
so there's this kind of conversation about dust being like a big problem, and we're going to have to figure out how to have dust mitigation strategies and filter that out in the cabin. But filters are inherently kind of a usable kind of material. They run out, they have to be either cleaned down, or they don't last forever. But you were talking about making fibers. There's basalt up there, so if you could make basaltic fibers, I was wondering, that's pretty similar to, say, like a glass fiber. They use that to make HEPA filter materials. It's a pretty established process down here. I was just wondering if there's opportunity for kind of like force spinning or spinning some basaltic fibers instead of using them for kind of structural properties, to use them to make kind of more complex materials that could be used in the longer term.
I don't see why not. I mean, the only thing that's governing, we're driving toward or about a 20,000th diameter fiber, and that's just based on the size of the little spinneret, whatever we call it, that we pull the we have a crucible, we basically, with a hole in the bottom, we pull the fiber out the bottom and cool it, and then coil it up. I don't see any reason why we couldn't make that hole smaller and go to much finer.
So how big did you say it was?
20,000.
Oh, sorry. I'm in Europe. What's that?
20,000ths of an inch. Oh crap.
That's all right. All right.
Okay. It's 20 thousandths of an inch. I'll let you do the conversion.
Cool. I'll use something I've heard of called Google.
Okay.
So I was also wondering, like, if you looked at any other methods of making kind of those kind of fibers, if you're drawing them, there's lots of different methods of making different diameter
Oh, sure. I
fibers.
can imagine. Yeah. What
If
diameter
you
are
want-
you interested in?
Oh, well, I think like the glass ones are usually kind of somewhere around the rounds of 30 microns and below.
Okay.
But I think I'm not sure. I think you could use force spinning for that. But I was just wondering, like, if there's an overlooked or kind of like it can be quite a niche manufacturing process. But if you've got basaltic, kind of, if you've got basalt up there, it could be an additional material that could be made that would allow more independence, should we say, or less reliance on resupply missions.
Absolutely. I don't know honestly, because that's my research area has always been in lunar, lunar concrete development and potential ways of reinforcing that. But I don't see why not.
Yeah, I guess once
It
putting
melts-
fibers.
Yeah, it melts at what, around 1150, 1200 C? Is that right, Jennifer?
Yeah, and that also depends on, what material you're using, basalts versus like highlands materials. and,
Yeah.
Yeah, it depends on your lithology, the rocks that are available at the site.
So I was going to say earlier, we were talking about, Karush mentioned that, you've got the materials that are available depend on where you land. So, we want to have a suite of materials, binders, for example, so that if we land here, we know we could make this kind of a binder to use for concrete. But if we land over here, we would need to change the binder because of a higher prevalence of certain materials. And Jennifer's the person to basically tell us that. She's got the master map of the moon in her office, so she knows where to land. I'm only marginally familiar with the spinning technique for making the fiber. I think I've seen some videos or something on YouTube about some commercial fiber developers. But I'm sure it could be done. I guess, did Gareth leave, or no, he's still here?
No, I just put myself on mute. Thanks.
Okay. Are you where are you located, Gareth?
I'm in the UK.
UK? Okay. I figured it was either UK or Australia, but I was going to, if it was Australia, I was going to suggest maybe some contacts there that you could potentially talk with that we've met in the past.
No worries. Yeah, it's cool. I think it's an interesting topic. I hadn't really twigged about that potential link, so I'll do a little bit more digging in my spare time if I can. Cheers. Thanks. It's been very interesting.
Great. Any other topics that anybody would like to bring up related to space manufacturing, or I'll say surface manufacturing? Tell you what, why don't we take about a 10-minute break, reconvene at 2:30 Central Time, and give everybody time to kind of refresh, bio break, and come up with some more questions. So I will meet everybody back here in about 10 minutes.